Welcome back. Let's talk about the reduction of carbonyl compounds to make primary alcohols. The first one that I want to touch base on is the aldehyde being reduced down to the primary alcohol. And I want to show you how we do this first with the mild reagent, then with the strong reagent. Alright, so this is the mechanism that you guys will need to be able to reproduce for any type of molecule. So right here I have a very specific aldehyde, one in which on the alpha position we have a sec-butyl group bound to it. But technically speaking, this is 1, 2, 3, 4. Okay, so this is 2-methyl butanaldehyde. But you don't need to concern yourself so much with the name. What's important right now is the mechanism of what we're going to do to this aldehyde. So when you bring your sodium borohydride, one thing that might be helpful for you to do or understand is that this is nothing more than an ionic species. The sodium is there to counteract the charge of the borohydride. And only one of those boron hydrogen bonds is hydridic. The other three are pretty much covalent. All right, so what happens is that the hydride bond, hydrogen and the two electrons attack the carbonyl carbon as depicted on the arrow there, and then the electrons of the carbonyl bond have to get out of the way towards that particular oxygen. So what this is going to do is produce an alkoxide, and notice right now that we have that hydrogen that we've just added from the borohydride. And the idea right here is that you started with one hydrogen because it was an aldehyde. Now you end up with two hydrogens bound to that same carbon. This is no longer an aldehyde, of course. This is now an alkoxide. Notice that now the sodium is associating with a negatively charged oxygen. This is still an ionic bond, so keep that in mind. This could easily be written as sodium plus and O minus with the 3 lone pairs around the oxygen. All right, then in the second step, all that you really need to do to yield the alcohol is to introduce an acidic enough substance like water. If you just quench this reaction by adding water, the alkoxide will attack the proton from water, and you'll end up kicking away hydroxide, which of course associates with the sodium plus to yield sodium hydroxide. And that also allows us to isolate the organic material right here, the alcohol material. So this is really the mechanism. You just add the hydride and then you protonate that oxygen. That's all there is to this thing. But I want to show you a little bit more intrinsically how this happens, because we do have that same aldehyde, reacting with the sodium borohydride. Now, typically when reactions do take place, there is a preorganization that kind of takes place in solution. And the interesting thing is that this preorganization seems to also form these cyclohexane type of structures. Now this one technically will be a cyclohexane type of structure because we have that carbonyl double bond. But what I want you to notice right here is that this is the aldehyde, and then directly behind it I've drawn the borohydride bond, and then we have the sodium right here interacting with both that oxygen and the hydrogen. So the sodium is kind of already positioning itself to accept the negative charge that it's about to generate on that oxygen. And notice that the boron hydrogen bond is already very, nicely located, very close to the carbonyl carbon to undergo the hydride insertion. So in the next step, what happens is that that hydride just attacks that carbonyl carbon, the double bond is broken, and then you form your alkoxide, and the sodium is already in place to accept those extra electrons. So you get that automatically, made for you, which is kind of nice. And your borane molecule kind of is still there in the periphery, um, you know, during the course of this cyclic process. So then at the end, when you add water, what really happens is that not only do you protonate your alkoxide to yield the alcohol, but you also um, quench your borane, turn it into boric acid. You get a little bit of hydrogen gas coming out of it, and of course sodium hydroxide, which is one of the byproducts of reacting alkoxide with water. All right, so this is something I'm going to use throughout the rest of this hydride reactions, just kind of to give you an idea of how these reactions are happening. And I'm calling this a transition stage because this is mostly a pre-organization of the molecules so that they're ready to attack, right? They're not necessarily representing the mechanism. In fact, notice that I don't even have curved arrows on any of these things. This is just to give you an extra layer of understanding as to what's happening here. All right, now primary alcohols can be made from aldehydes, and you could use either sodium borohydride or lithium aluminum hydride to carry that reduction. But you could also start with either a carboxylic acid, an ester, or an acyl chloride. And if you do want to make the primary alcohol, then you have to react either of those three molecules with lithium aluminum hydride, the strong reducing agent. Okay, so using sodium borohydride here will have no effect on those particular molecules. All right, and just got to remind you, right? So you have your aldehyde that can still be reduced with your lithium aluminum hydride in the same manner. You attack the carbonyl carbon, the electrons of that double bond CO bond, move towards the oxygen to give you a lithium alkoxide. You have now introduced a new H on the carbon, and then you protonate with water, right? So you have the alkoxide attacking one of the protons of water, and you produce lithium hydroxide. And very similarly, you have that pre-organization of aluminum hydride, right next to that aldehyde molecule. Once again, I've drawn it so that it's behind the molecule, but this could also be drawn from the front of the molecule. There is no preference for either side. So if you end up producing a chiral carbon, it will be racemic, and that's a big point to be made here. But the same thing happens. You have the lithium, already nearby the oxygen, kind of waiting for that oxygen to develop the negative charge, and the hydride is positioned, directly in front of that carbonyl carbon. It gets given to that carbonyl carbon. You produce your alkoxide, and once you add your water, you of course produce the alcohol, but you also destroy the rest of the aluminane that you have in there. You produce alumina or aluminum oxide and hydrogen gas in the process. All right, so now let's see how. Now that we've seen that, yes, okay, we can do the same thing with the aldehydes. Let's see what happens when we start with an ester and we treat it with lithium aluminum hydride. As of now, we're claiming that we're going to go all the way to the primary alcohol, so we need to see exactly how that's going to take place. All right, so we're going to start here with the following ester. We have an isopropyl group on the left side. We have ethoxide on the right side, right? And since that ethoxide is bound to the carbonyl, this is definitely an ester. All right, so the mechanism basically follows similarly to what we saw with the aldehydes. The hydridic aluminum hydride bond attacks the carbonyl. The bonds of the CO double bond move towards the oxygen to create an alkoxide, technically speaking. Lithium alkoxide, since what we start here is lithium. We also kick away aluminane out of this thing. All right, now this is the part that is going to look very funky to you right now, because as of now, what we've been telling you is that you have to have a good leaving group if you're going to do some sort of elimination. If something is going to come off carbon, it better be a leaving group. And as it turns out, what we're about to kick away is not a leaving group. Specifically, what's going to happen is that those bonds of that lithium alkoxide are going to come back down to reform the carbonyl, and out of hydrogen, carbon, and oxygen is the only thing that's remotely, okay in terms of a leaving group. And by the way, it's not okay, but compared to the hydrogen and carbon, that's the best alternative. So the ethoxide actually serves as a leaving group in the formation of the carbonyl. And of course, notice that you still have the hydrogen and carbon. So the moment that carbonyl gets reformed, you have now produced the aldehyde, which is that midway between the ester and the primary alcohol. And we have kicked away lithium ethoxide. In a minute or two, I'll show you why this actually happens and what tends to help lithium ethoxide to actually come off as a leaving group, right? But first, let's finish the mechanism. So you have now freshly produced an aldehyde, but the deal is this: you can't stop at the aldehyde stage because you are using lithium aluminum hydride. Even if you weren't using aluminum hydride, the aldehyde is already good enough to be reduced down to the alcohol level. But the fact that you have aluminum hydride, the moment this aldehyde gets formed, is already getting attacked by that aluminum hydride, and this will be a second equivalent, of course, of that reagent. So we attack the carbonyl carbon, the electrons of that CO double bond move towards the oxygen, you now form the alkoxide. But notice that now we have introduced two hydrogens on that very carbon. And in the last step, of course, once we add water to quench the entire reaction, the alkoxide accepts the proton from water, lithium hydroxide is produced as a byproduct, and now you produce your primary alcohol. But this all occurs because midway through the sequence we are forming the aldehyde, right? And we already saw that the aldehyde is going to produce a primary alcohol, so this is really no different than that. But what I want you to notice in this sequence is that in the first step you have what we call an addition process, right? We are adding the hydride to the carbonyl. You break the CO double bond before the leaving group takes off. Now the double bond gets reformed, and when that happens, that's when the leaving group takes off. And that's the second step. We call that an elimination step, not to be confused with elimination reactions like E1, E2. This is just an addition elimination. In fact, these two steps sometimes are treated as almost one sequence entirely, and we just call this addition elimination. But that's just specific. That's not very useful to us at the moment. And the next step, we have another addition, this time an addition to the aldehyde that we have formed in the course of the first two steps. And then the final stage is a protonation, right, to yield a neutral organic material. And whenever you're doing mechanisms, this is what you're after. You want to make sure that you end up with a neutral organic material. If your organic substance has a positive charge or a negative charge lingering, you're not done with the mechanism. You got to get to that final neutral state. All right, now here's what I'm going to try to explain to you how this happens. We have to look at those transition states to make sense of this madness. And in the first sequence, right, when you directly react the ester with lithium aluminum hydride, you could envision the ester positioning itself the way you see right here, literally on the plane of the screen. And directly below or behind it rather, I have my aluminate present, ready to attack. The hydrogen is positioned very close to the carbonyl carbon. The lithium is interacting both with lithium aluminum hydride but also with the oxygen in anticipation for formation of that negative charge. And then once that adds, what ends up happening is that you form your alkoxide, right? And that alkoxide is now associated with lithium. But now a new molecule of lithium aluminum hydride comes in, and notice it's right here. That's your LH4, and here is your lithium, your new lithium molecule. All right, so what now happens, interestingly enough, is that your ethoxy component of what used to be the ester is now interacting fairly well with lithium. And because lithium is now interacting with ethoxide, it makes it feel more like a protonated ether, which is a good leaving group. It's not as good as that, but it's somewhat mimicking that scenario, to the point where now the molecule says, well, heck, this is not too bad of a leaving group. You got the lithium there to passivate that negative charge, so you're making it a little bit more likely for it to come out of solution. And so here's where you have that rearrangement. The electrons of that lithium alkoxide move over to reform the carbonyl compound, which now will be an aldehyde, and then these electrons will move over to make your lithium ethoxide side product. Okay, now and of course here on the back you have your aluminate that is ready to come off, right? Because that already yielded the aluminum hydride. But notice that the lithium aluminum hydride that came in here, it didn't get used up. It just came to kind of provide that extra lithium to allow the process of elimination to take place Uh, but notice that you also had this other extra lithium there that was also interacting with your aluminum hydride. So that, basically all that happened here is that one lithium got exchanged for the other, and you still have the lithium aluminum hydride lingering. In fact, it's basically ready to now react with the aldehyde that we just formed. And here, we get the same picture as before. Here's your aldehyde. You get your aluminum hydride positioning itself to have the hydridic hydrogen attacking the carbonyl. Lithium is right next to that oxygen. So once the hydride is directly covalently bonded to that carbon, you form your alkoxide with lithium, right? And protonation at this point will simply yield your alcohol molecule. Aluminum will actually get completely destroyed into alumina. You also produce hydrogen gas and your lithium hydroxide. So this is how the whole process takes place. And here you can see a little bit more clearly, well, okay, that lithium is definitely facilitating the ethoxide as a leaving group, right? And it's still not the greatest thing, but it's good enough. It's good enough for this molecule now to remove it. Now, one thing I want to tell you though is that this is the way I think of the reaction. I don't want you to assume that this is the official, mechanism with all the proper transition states, but this is what makes sense to me in terms of what's present in solution and what's actually doing chemistry. And it might help you kind of visualize how this thing really happens. Why are we breaking these rules that we've kind of like come to treat as the rule that we don't break. Well, this is why we're breaking it, because we are kind of bypassing that problem that we had before by having lithium kind of withdrawing electron density from your hydroxide. Okay, now let's see what happens with carboxylic acids. All right, so carboxylic acids are actually not all that different from esters. But the one key difference is that you do have a highly acidic proton, right? This is, in fact, more acidic than most other protons that we've seen in molecules so far. So the very first event that takes place between lithium aluminum hydride and your carboxylic acid is nothing more than deprotonation. The hydride is going to go after that acidic proton. The acid-base chemistry, the pKa's, are basically completely against you on this one. The protonation is what's going to happen first. Sometimes this particular feature, and of course the electrons here of the OH bond will go to the oxygen to give you a carboxylate. This particular feature sometimes gets kind of overlooked in most textbooks, and it kind of drives me nuts because that acidic proton is not just going to hang around when you bring something that's technically strong base. This is hydride. Hydride is the conjugate base of H2. And that's got a pKa of about 35, right? And your carboxylic acid barely has a pKa of about 4. In this particular case, it's probably going to be a little bit lower than 4 because you have that sp2 hybridized carbon directly bound to your carbonyl. But regardless, this process is going to happen, right? There is no avoiding it. So you will produce some hydrogen gas in this first step. Now, in the second step, that's when you actually carry out the addition reaction. So a second equivalent of lithium aluminum hydride has to be used to attack the carbonyl of the carboxylate. And this is the reason why you have to use a very strong reducing agent, because you already have a negatively charged species and you're trying to add another negative charge to it. This requires the use of a heavy lifter. So attack the carbonyl, move the electrons away to the oxygen. You now have these two lithium oxide bonds present. All right, and then you have your aluminum that also comes out. All right, so here basically what needs to happen is that one of the oxides needs to come off. So you could think of this as moving the electrons of that lithium oxygen bond back down here to reform the carbonyl, the same way that we did for the esters. But now the leaving group is an even worse group. Now we're having to kick away oxide, which you would think this is not possible. Like, no way. Okay, ethoxide, that's one thing, maybe. But an oxide, you're going to kick away an oxide? How is that even happening? And we won't be able to tell that just yet until we look at the transition states. But for now, just follow my lead. We're gonna reform the carbonyl. We're gonna kick away the oxide, and of course, we have that lithium ion above present. So this will be removed as lithium oxide, 2 lithiums, 1 oxygen, and this forms your aldehyde, which then gets treated with a third equivalent of lithium aluminum hydride to attack the carbonyl carbon, produce break that CO double bond and produce your lithium alkoxide. So now you have added two equivalents of hydride to that carbon. And of course, the last step is always protonation. Bring water, protonate this thing, and produce your alcohol. All right, so needless to say, you have to use more than just one equivalent of lithium aluminum hydride. In fact, excess amounts are kind of required just because you're going to lose one equivalent in the first step due to the protonation. All right, now let's see how the transition state can help us understand what the heck's going on here with the aldehyde, at least the formation of that aldehyde. All right, so if you think about your carboxylic acid, and I'm drawing it right here, you can see it right there, carboxylic acid, OH bond drawn out exactly. This can start interacting with your lithium aluminum hydride in, a model that may look somewhat like this. Now that hydride is interacting with the acidic proton of the carboxylic acid. It attacks that proton and produces the carboxylate, kicking away the hydrogen, right? So in the process here, you have electrons going to oxygen. The oxygen kind of rearranges itself to reform the double bond over here. And at the same time, you will be now turning this carbon-oxygen double bond into a single bond that interacts with the lithium over here. And so this will now give you lithium carboxylate, which has its oxygen interacting with aluminane, which is the byproduct of this reaction. All right, now imagine bringing a second equivalent of lithium aluminum hydride to this mixture. What will happen now is that here you have your lithium interacting with both aluminum hydride and also oxygen. You have the other bond here, the hydridic hydrogen, positioning itself right next to that carbonyl carbon. And if we have everything else here on the left side, what you will notice is that once that proton gets added to the carbonyl, we'll get that diol, or technically diolate, intermediate. This is now aluminane. We have lithium, we have aluminum, another lithium. But what I want you to pay attention to is the fact that this oxygen here on the back is right now bound to lithium plus, but it's also bound to the electron deficient aluminum with 3 hydrogens, right? So that lacks 2 electrons. It can accept 2 electrons from the oxygen, and by doing so, we're basically diluting away the negative charge of the oxide. So now it doesn't look as bad as we thought before, because O minus coming off, that's a crazy story. But if we have lithium binding to it and we have aluminum also binding to it, we have basically kind of a dilution of that charge and maybe a sequestering of the strength of that bond. So both of those metals in conjunction, what they can do for us is that now this alkoxide can come back here to reform the carbonyl carbon, now containing a hydrogen and a phenyl group bound to it. And at the same time, this oxide can finally take off with the aid of aluminum and lithium to ultimately form your lithium oxide. So from this event, we can kind of see, okay, this doesn't look so bad. And needless to say, once you add your lithium aluminum hydride, that can interact with the aldehyde that we form right here to yield your alkoxide, which upon protonation can yield your alcohol. All right, so everything kind of falls in place right here. And I'm going a little bit out of my way to show you how I think of these reactions because it drives me nuts that textbooks don't care to show you what happens in these events. They just kind of tell you, oh, if you react this with excess aluminum hydride, you're gonna get the primary alcohol, and end of the story. And even though that's useful and for synthetic chemists that's good, like sometimes we just want to know what can we use to make this thing, without necessarily considering all the steps that make it happen. This is a good way of kind of validating the knowledge that we already have, that certain groups that are considered bad living groups can be turned into good living groups if you add the right components to it, right? In this case, aluminum, electron deficient aluminum, and lithium plus together can allow us to break that oxide away from the original carboxylate molecule. Okay, so that's all the story for making primary alcohols. You still need to be on on point about the mechanisms. I don't need you to necessarily know the transition states, but they kind of help visualize what's happening. But be on point with your mechanisms. In the next video, we're going to talk about the secondary alcohols and aldehydes. So see you then.